This is my Module B portfolio. For this first IQE for B1, I kept the same question. I was happy with how this question turned out. So same solution. I did, though, add that diagram. I thought it would add more context to the problem and would be better to visualize the actual problem instead of just talking through it. So you can see they remain the same. Um, so the pressure was then so this conceptual was also the same. I was also happy with the content in this and the explanation associated with it. For B2, external drag and pumps, I decided to rewrite the whole calculation problem. So for this one, a baseball with a diameter of 3 inches is hit in the air with an average velocity of 98 miles per hour, and a wind is blowing on it at 15 miles per hour. If the ball travels in the air for 3.5 seconds, what will the work done by the friction from the air be? And then assume the ball to be not a perfect square, but a perfect sphere. That's a little bit of a miss right there. Perfect sphere. So we have our perfect sphere ball. We show the two velocities of both the ball and the wind there. So our knowns, we have our velocities, and we're finding our work on the ball, assuming the ball is a sphere, and the wind is a steady flow. And then we have our properties of air. Then to our solution, first we find the relative velocity of the baseball, and we're going to do this in metric units just for simplification. So we take the velocity of the ball, subtract the velocity of the wind, and get 37.1 meters per second. We will convert our diameter and areas into meters and meters per second respectively. And then we'll find our Reynolds number for the flow of the ball. This is so we can find the actual drag coefficient on the ball, and we find that our Reynolds number is a high number. It'll be between the 10 to the third and 10 to the fifth Reynolds numbers for high flow drag. So the CD will be constant at around 0.5. And then with that CD, we have that drag coefficient, we have all our variables defined, and we can find the force. And then we know the definition of work is force times distance. So by finding the distance the ball travels in that time period, we can find the work done, the average work done, no, the total work done on the ball over that time and force. For this one, I just simplified the conceptual a little bit. I was asked in the original conceptual question, the friction for it was pretty vague on what the question was asking, and so now here we're asking how the friction force would differ. And there's the answer. I kept the answer about the same, discussing spins on the ball and how the seams would make the ball less of a perfect sphere. So this question, I also kept the same. I got a relatively good feedback from it. I liked what this question was asking. So same answer to it. I did include more units into the plugging in the numbers there. I thought plugging in the numbers would add more context to where that final answer came from and was just more useful and was a better explanation for where that number came from. So the conceptual for B3, I So I reworded the question a little bit just to be a little clearer. It reads, if the filter were changed for one with a smaller pore size, how would this affect the flow? Generally the same question, and so the answer is about the same. You know, the filtered rate's going to be faster, speed up the process, and there's a little more discussion into how, you know, going faster with the process may be detrimental to the actual or to the end goal of the process due to lack of filtration. So for this IQE, this is a brand new IQE and problem set. I did not do the B4 problems. Conceptual asks, you are working on designing a compressor which expels hydrogen gas through a converging nozzle to atmospheric pressure. You want to know whether the flow is choked. How would you determine if it is choked? So, you know, the explanation, flow is choked. To know whether the flow is choked, you're going to measure the velocity of the air coming out of the nozzle, and then you're going to find the Mach number between that speed of sound of the air conceptually and the velocity actually coming out. And if it is equal to 1, the flow must be choked. And then this choked flow means that mass can't be increased through the nozzle. So for the calculation problem, we're determining the velocity. The velocity of the hydrogen gas is determined to be 537 meters per second, and you want the flow to choke. If again the pressure out of the nozzle is atmospheric and the temperature at the outlet is 40 degrees Celsius. So we're going to determine what the current pressure is coming out of the nozzle, and if the flow isn't choked, what must the pressure be? So our knowns, we have our temperature and pressure and our velocity, and we're going to find the pressure in two cases. We're going to assume the nozzle is isentropic. This is going to make our equations a little easier, and we're also going to say that the gas has negligible velocity coming into the compressor, meaning our pressure at the inlet of the compressor will be equal to a stagnation pressure. And then properties of the hydrogen gas, our solution. Well, we have our temperature converted to kelvins, and we're going to find the speed of sound through that square root KRTM. Speed of sound is around 1300 meters per second. And then we determine the Mach number, and that is going to be 0.4 with gas exiting at 537 meters per second. So this means the flow is not choked. We can determine from the table with literature values the pressure, and so we're going to find that P stagnation, which will be equal to the inlet pressure. So in case 1, that's going to be around 113 kilopascals. And then if we want to increase that flow to choke flow, the Mach number will be 1, and thus that ratio will be different of P over P naught. And this newfound P naught will be around 191 kilopascals.